instruments are in tune. They both are playing a frequency around 390 hertz. So they're in tune, but they sound very different. The question is, why do they sound so different if they're playing the same note? And the reason is they're not playing a single note. They're playing a collection of notes. Okay? So when you hear a tone, when you hear a note, you typically are not hearing a pure tone. You're hearing many tones. Okay? So the analogy would be if I were to ask two people to go home and make their favorite spaghetti sauce from scratch, they probably would taste different. And the reason being is that they might use different ingredients. That would be expected. But if I said, you must use a certain brand of tomato paste, and you must use salt, and you must use pepper, and you must use garlic, and I give them the list of ingredients they must use, they go make their spaghetti sauce and come back, it likely would still taste different, even though they use the same ingredients. And the reason would be they might have used different amounts of the different ingredients. And that's the key. And so similarly, sounds can sound very different. Even though they have some of the same ingredients, they may have different ingredients, or they might have the same ingredients but different amounts of the different ingredients. Okay? So now, when you play a string, that first instrument was my banjo, and when I was playing that string, you have the fundamental frequency. Okay, now that's not just one tone. It's not a pure tone. If it was a pure tone, it would sound more like a whistle. But it's not a pure tone, it's a string, and that string has many notes, and the fundamental is called the harmonic. So if the fundamental has a frequency of F, then you'd also hear the second harmonic, which would have a frequency of 2F, and then the third harmonic, 3F, and 4F, and 5F. You hear them all in different amounts. Usually the lower ones are the stronger ones. Okay. Now, if you heard an open pipe, the same sequence, F, 2F, 3F, likewise. But the second instrument I played was a closed pipe. It was a piece of PVC pipe with a rubber stopper in the end, and it is a closed pipe. And the closed pipe doesn't give you the even harmonics. It gives you the odd harmonics. So if your first thing you would hear would F, but you'd also hear 3F and 5F. You wouldn't get the 2F and the 4F. You have different ones present. And that's part of the reason why the banjo and that pipe will sound very different. Now, how do we actually measure this? Okay, how do we measure this? How does it get this sound? Well, the effect of this sound is what's called the timbre, although it's spelled Timbre. It looks like timbre, but it's actually pronounced timbre. The timbre of that instrument is made up of many different things, part of it being all the different harmonics and relative strength. But how do we actually measure those things? Well, we can actually do it in real time using a program, an FFT, do the analysis, a fast Fourier transform. The app that I have on my phone that I'm going to use is called FFT Plot, and I'm going to let you see that for these two instruments. The app we're going to use here is called the FFT Plot, and what it's going to do is it's going to give you a graph of the different frequencies, basically the spectrum of the frequency of the sounds it hears through the microphone. Now, a pure tone would be one frequency, and a whistle is pretty close to that. So that one spike is the one frequency. If I use a lower pitch, it's a pure tone. But now let's listen to the two instruments, the banjo and the closed pipe, again, but now we're going to focus on the pure tones that make up its timbre. So you'll see many spikes there, and let's analyze that. Let's take a look. Let's listen to it. And now that we've frozen it, now what we can do is we can just touch the screen and we can figure out the frequency of each of these. So the first frequency was around 390, and then for a string, the next harmonic should be about 780. That's twice the frequency, twice the fundamental frequency. And then the third harmonic should be at about 3 times that frequency. Which is about 11. About 1170, and then we can go to 4 times that, around 1560, and 5 times that. Okay, so we can get the different frequencies that are present. They're just integer multiples, the fundamental 1, 2, 3, 4, 5. But now let's listen to that pipe. And it's going to have the same fundamental. But we'll notice here that we get it at, once again, around 390. And then we come out here and we don't get the 700, which is twice, we get 3 times. And then we get 5 times. We get 1, 3, and 5, the odd integer multiples, rather than the 1, 2, 3, 4, and 5. So these two instruments have the same fundamental frequency, so they're in tune, yet they sound very different. You can hear it with your ear. The average person can tell, yeah, one's a pipe, one's a guitar or a banjo in this case, but they're in tune, but they sound very different. Most people can hear the difference, but they don't know why they hear the difference. All right, the amp we're going to use here is called the FFT plot, and what it's... All right, now, how do we apply this? Well, it gets applied a lot in terms of, say, a synthesizer. And so you might say, well, how do we get a electronic instrument to sound actually like a trumpet? Well, they electronically mix it to match the FFT of a typical trumpet. In fact, you can go as far to say, I want to sound like Miles Davis, or I want to sound like Dizzy Gillespie or Louis Armstrong. You can actually, get those types of mixes. They sound very much like a particular type of player. Okay. It also applies when you say want to do voice recognition and different to make things sound like a particular voice, or to test a voice, because everyone's voice has a different fingerprint, so to speak, and it comes by looking at the FFT, different vowel sounds, the A, E, I, O, different vowel sounds. They have a different FFT, and so they can synthesize and have electronic sound voice, which is generated electronically simply by replicating the tones that are present in any particular vowel sound. Okay, so hopefully that'll help you a little bit understand timbre and how that relates to music and the physics of that.